Sometimes you find someone panicking when they're actually seeing exercises such as this one. Let's say you have questions like you have a bacteria culture that is growing with a constant relative growth rate, and the bacteria count was caught at 400 after 2 hours, and it was 225,600 after 6 hours. Now, the question is, what is the relative growth rate? Express your answer as a percentage. What was the initial size of the culture? Find the expression of the number of bacteria after 2 hours. Find the number of cells after 4.5 hours. Find the rate of growth after 4.5 hours. When will the population reach this much? And some other questions will be, you have a population of a micro BR culture which grows by 2.5% every day from an initial population and not. Which of the following exponential function describes the culture's population at any time t? And then you have to make a choice here, or you have to rewrite that with some base e. What will be the growth rate in such cases? Or someone decides or they want to decide whether 40,000 investment for 4 years, whereby the money will earn 12% compounded monthly. They want to find out what will be the investment after 4 years, or will the investment be worth it, or should they consider other options. Or you have a half-life of a carbon 14, which is approximately 430 years, if a sample original contains this and that and that. Now, you find out these problems. Most students or scientists who want to solve them, they panic when they see that. The reason for that is because they usually find out that they don't really see what is the meaning of the topic that actually deals with these problems. So the first thing I want us to do here, I want us to first look at, because I want us to look at the topic itself and see if we can get some information there to actually solve these problems. Right. The topic that contains these problems is exponential. Let me use that one. Exponential growth and decay. Right. Now, what is an exponential growth and what is exponential decay? Let me write it down. We have exponential growth. What do we mean by that? The meaning of an exponential growth means that you have a quantity. So I'm just going to say quantity. You have a quantity that is, first it must be growing. That is growing at a constant rate proportional it is growing at a constant rate. It is growing at a constant rate, and that rate is proportional to the current, or let me just say initial value or initial size. So we actually have this quantity. It is actually growing. It is growing. You can say it is growing at a rate, constant rate, proportional to the size. So it's growing. I can say growing or increasing. That's what is important here. And then the exponential decay. We have an exponential decay. What is an exponential decay? An exponential decay is when you have a quantity. That is decreasing, the opposite of increasing, decreasing at a constant rate proportional to the current size, or let me say initial size. That's what this is all about. And now, what is the application of exponential growth? Exponential growth, we will find out that, let me just have this blue pen here. I'm just going to talk about the application. You can either be having a bacteria, you have a bacteria growth, you see the application there, or you can see that when you have population growth, or when you are actually having compound, and this is compound interest, right? Bacterial cells, when they are growing proportional to the size, or you have a certain population that is growing, or you have a compound interest, you have your money is growing. And then when it comes to decay, let me use the red because something is decreasing here. You will find out that its application is when you are actually dealing with a radioactive decay, or you actually have cooling objects. You have cooling objects. That's where you will find the application of that, or when you have assets that are depreciating. Assets are depreciating. So one important application of this is when we're actually looking at how old an animal has existed in this planet Earth. So basically what usually happens, if an organism is still living, it keeps consuming carbon-14, and then when it dies, the carbon-14 keeps being converted from carbon-14 is being converted to nitrogen-14. And now if you can measure how much of that carbon-14 is left, then you can actually see how long has that organism lived on planet Earth. And in most cases, we found this carbon-14 in a bone. So that's one of the applications that usually happens here. Now let's look into this at an actually deeper details here. Now before we do that, I want us to actually look at the notation. Now N0 or N0, we usually say this one is the initial. This is initial amount, or we usually say principal amount. The amount that we're starting with before anything happens. And then we also have I, and I in this case, we're just gonna say it is an annual interest. And then usually this, we want it to be in decimal places, so it's a decimal. And then we also have N. Our N is going to be the number of compoundings. And then we also have T. T is usually time. Sometimes it is in years, sometimes it is in days, sometimes it is in something else. For now, let's just say in years. And then here we also have NT. Our NT here is going to be the total amount after T years. Right. Now, what is basically happening with this? I want to add some pages here and then see if I can. I was just adding the pages. Now that we have this, I want us to find the formula of NT. Right. The formula of NT. This is what I want us to find. Now, I'm going to break this into two pages. I'm gonna break this page into two, and then this side I want us to have growth, exponential growth, and then this side I want us to have a decay. Right, now what I want us to do first is, if let's say we have n of 0, that means when the time is still 0, we haven't started anything, n of 0, we say it is equal to n naught, and also this side, when t is equal to 0, we still have the same amount we're starting with, so we're supposed to have n0. Now, when t is equal to 1, so we have n of 1, we're supposed to have the initial value. Remember that now we have a quantity that is growing, so we're gonna have, if it was money, we're supposed to have n0 plus some profit if this quantity is money. Or if it is not money, it's just some another amount, I'm just gonna say it is n0 plus some change after a year. Right, if let's say t is in years, after a year we're supposed to have n0 plus some change. But at this side, because the quantity is decreasing, so our n1, that is after some time t is equal to 1, we're gonna end up having n0 minus some change, so it is reduced by that much. Now, going back to the definition of exponential growth, we said that this growth is proportional to the current size, right? Now, the current size, like initially at the beginning, we have this. So we wanted to rewrite this in terms of this n here, n0. Now, before we do that, this change we usually represent it by a delta. This change here, we're gonna represent it by a delta, right? So this is just n0 plus some delta. This delta is just saying the change. Now, I want us to rewrite this change in terms of n0. You can see that there is not, we don't have any n0 here, and we also want to write this proportional to that as a fraction. So we're gonna say n0 plus delta, and then you divide by n0 here. But we did not have any n0 here, so we end up multiplying by n0, so that this n0 and that n0, they cancel out, and then we are left with that. Why are we doing that? Is because we wanted this part here, which is saying that this change here is proportional to the current value. The same thing here, we're also gonna have with the decay, we're gonna have n0 minus some delta, just a change. And then here we're gonna have n0 minus delta divided by n0 times n0. Now, when you look down into this divided by that is just some interest in a decimal place. So you end up having a 0 plus some I times n0. This I here is representing the change divided by n0. That's the I. And then we have this n0 this side. And then this side we will end up having n0 minus I times n0. And if you take the common factor here, we'll end up having n0, and then we're going to have 1 plus I. When you're factoring out n0, n0 divided by n0 is 1. I times n0 divided by n0, we have an I. And this side, of course, we're going to have n0. If I take this n0, I'll be left with 1 minus. If I take this n0, I'll be left with n I there. This simply means that n of 1 is equal to n0 into 1 plus I raised to 1. And then this side I will have n of 1 is equal to n0 into 1 minus I raised to 1. Note that this one and that one are the same. Now, when you look into this, you will find out that now I want to find, I'm done with this part, I'm done with that part, what will be n of 2? Remember that n of 2 is going to be the current amount plus Okay, I've just exhausted my space here. Let me just still divide here, and then here will be, we're gonna have our current amount plus the change, and then here also n of 2, we're gonna have the current amount minus the change, right? So here we'll end up, the current amount now is going to be n of 1 plus some delta there. And then if you look into this n1 is the same as n, let me just finish this up. And then if I want to change this, I will end up still having an n1 plus delta divided by n1 times n1, because I wanted this to be proportional to that. I want you to note that this change here, let me just put a hat there, just a little hat, to say that this delta is not the same as this delta there, but this delta here is proportional to n of 1. So we have this delta divided by that, and of course, because the rate is proportional to this, in other words, whatever the delta was compared to this is still our I. So we're going to have n1 plus I times n1, because the rate is supposed to be constant, so this is still the same as I. The same thing this side, I will end up having n of 1 minus delta, and then you divide this by n of 1 times n of 1. And then here I can factor out n of 1, and then I'll be left with 1 plus I. This is n, this is just n1, and then we have n1. When you're taking it out, we're left with that. And then this side also, you will end up having n of 1, and then when you're factoring it out, this is gone. I'll be left with 1 minus, and then this side here, I will be left with this portion here. Take note that this portion is the same as I, so I will have minus I. But if you look into n1, we said that it was equal to n0 plus I this side, so we have n0 into 1 plus I times this 1 plus I there. And then the same thing this side, I will have n0 into 1 minus I and times 1 minus I, which is this. So I just replaced this by that which was our n1 in the decay. Now, if you look into this, you will find out that we have n0, and then we have 1 plus I all raised to this and that. We have 2 of these. Let me go down. I'm trying to divide this page here. Yeah. And then this side, you will find out that we end up having n0, and then we have 1 minus I all raised to 2. If you continue here, you will end up, let me just say, n of 2 is equal to n0, 1 plus I to the power 2, and then n of 2 this side, we have n0, we have 1 minus I raised to 2. Right. And then now, we are saying that, okay, we understand n of 2, and now we are looking at n of 3. N of 3 is going to be n of 2 plus some delta. Let me put a star there. And for the decay, n of 3 is going to be n of 2 minus some delta star. And then if you look into this, what was n2? Let me still keep it for now. And then here I want to write this as a proportion of that. So I'm going to have n star, and then I divide that by n of 2, because this was not there here. I have to multiply by it again. The same thing this side, I was n of 2 minus delta star, and then I divide by n of 2 times n of 2. That's what is really happening here. And then when we go further, because this, we said it is growing at a constant rate, that is proportional to the current value. This is the current value, so this must be I. So we're going to have n of 2 plus I times n of 2. And then this side, of course, you're going to end up with n of 2 minus I times n of 2. And then if you're factoring things out, you will end up having n of 2. And then here we'll be left with 1. If I take n of 2, I'll be left with plus I. And then this side, if I take n of 2 out, I'm factorizing it out. I will end up, take this out, I'll end up having a 1 minus some I. So I have this, I have that. What was n of 2? N of 2 was equal to that. It was equal to n naught. I have 1 plus I, or raised to 2. And then I have to multiply this by 1 plus I, which is this. So I replaced this part by that part which was there. And then now you can see that we end up having n naught. This and that is the same. When multiplying powers of the same base, you add the exponents. So we'll end up having 1 plus I raised to 3. And then here we'll end up having the same thing as n naught into 1 minus I raised to 2. And then I multiply by 1 minus I. And this is going to be n naught into 1 minus I raised to 3. So I have that. This simply means that whenever you have n of 3, you're always going to have that. And whenever you have n of 3 in decay, you're always going to have that. And one can actually notice that this 3 goes with that 3. This 3 goes with that 3 on that side. This 2 goes with that 2. This 2 goes with that 2 that side. And this one goes with a 1, and this one goes with a 1. So we can generalize this and say that actually our n of t, let me just proceed here. Our n of t is just the same as n naught into 1 plus I raised to some t there. And this side, our n of t for decay, we're going to have n naught, and then we're going to have 1 minus I raised to t. So this is our formula here, usually called compound interest formula, and this one here for the decay. So we have these two formulas. Just a quick recap before we move forward. We said that we wanted to talk about exponential growth and decay. What is an exponential growth? An exponential growth is when you have a quantity that is increasing at a constant rate proportional to the current size, right? If we are starting at the beginning, it is an initial value, right? Now, the exponential decay is when you have a quantity that is decreasing at a constant rate proportional to the current size. So n naught, we use n naught to denote initial amount or initial size, and I is the annual rate. Let me put some star there, and then n is the number of compoundings, and t is time in let me say in years. Most of the time t is in years, and nt is the total amount after t years. Now, I want us to talk about this. The reason I was placing a star in I and also in T, this is a Y. Let me try and give you a Y. If I is per year, we have I is per year, that is per annum, right? It's an interest per annum or per year. And T is in years. The formulas we use is going to be NT is equal to N naught and then 1 plus I raised to T. And then for decay, we're going to have N of T is equal to N naught and then is 1 minus I raised to some T. If I is per annum and T is in years. Now, let's also analyze this. This is the first one. If I is per day, right, we're receiving this interest per day, and T is in days. So if I is in per day and t is in days, still we use the same thing. So we're going to have n, but t would be in days, and we have I naught, and then we're going to have 1 plus I and t. That's it. For decay, we just have a minus there. Now, if we have I is per, let's say, per month, and t is in month, then we have t is we have I is per month and t is in month. Then the equation we're gonna use is going to be nt is equal to n naught, and then we're gonna have 1 plus I raised to t for growth, and then minus here for decay. If I is per quarter, let me say per quarter, we have per quarter, and t is in quarters, it's in every 3 months, then the equation we use, we still if t is in quarters, or let me just say here so that it is clear even to you, if t is the total number of quarters per year, then the equation we're gonna use is still nt is equal to n0, and then we have 1 plus or minus I raised to t. So we'll end up having the same equation if we have I is per day and t is is a number of quarters per year. We use the same equation as that. Now, where will we actually encounter problems here? I want us to analyze this equation so that we can actually get to know how to use it. Now, if, let's say, I is per, this is about to be n, per annum, that is per annum, right? We have this per annum, and t is in days. What is it gonna happen now with the equation? So this one is given per annum, but t is in days. In other words, we are receiving a portion of this interest every day. What this usually is usually asked, or it is usually given, we just say I is 10% per annum compounded daily. Now we have daily, that is an issue, which means that you have this interest is in per annum, but t now is not the number of years. Per annum means every year, and then this t now is they're saying compounded daily. They are saying that you are not receiving this interest every year, you are receiving this interest, you are receiving a portion of this interest daily. In other words, t must be in days. So which formula are you actually using? We had the original formula, which is saying we had n naught, and then we have 1 plus I raised to some t there. But now this t here is supposed to be now, because compounded daily, we want t in days. If t is in days, we're gonna leave this t as it is, but now 10% is per year, so we have to divide this to find out. This is like this. After a year, I want you to get 10%. But now, how much will I get in one day? Because this is saying daily, which means I will give you a portion every day. So I wanted to know how much of this will it be for a day. If I multiply 10 by something, I'll get something bigger. So I have to divide because I want a slice here. So I will have to divide by how many days per year. So I will have 365. and then I leave that if t is in days. If t is in days. If t is in years, then I will say 365 times t, the number of years. So you end up having something of this kind. Another way will be if you have your I, and I is per annum compounded monthly. Right. And if t is in month, then the equation you will end up using is going to be t is equal to n naught and then 1 plus I raised to some t there. If t is in days, but now this one is saying, I will give you this per year, but compounded every month. How many months do we have per year? That's what we put here. We have 12. And if this is already in month, we'll leave it like this. But if it is not, let's say it is in years, we have to multiply by 12 there. Why is that so? It's because we are receiving interest, a portion of that every month. That's the meaning of a compound interest. Now, we are trying to analyze this whole thing, but in a shortcut, I would just say this. N of t is always equal to n naught, and then you have 1 plus I divided by n, and then you have n times t. If t is in years, I is per annum. This n here is saying how many times per year are we receiving a portion of that interest. If someone is just saying I is equal to 10% per annum, this per annum is PA, which means that, okay, I'm receiving it once. This n here will be 1, and here it will be 1, and we leave it, the formula, as the original. If someone is saying n per annum compounded, that compounded is saying to you that, yes, per year you're going to get that, but you will receive interest in portions every n times. So you have to ask yourself, how many times per year am I going to receive a portion of this? If you're going to receive daily, this n is the number of days per year. If they're saying compounded monthly, this n here will be the number of month, which is 12. So you're going to have a 12 and a 12, and then it's number of years. If they are saying compounded half yearly, how many hours per year? Here will be a 2, and there will have a 2. That's all there is to the analysis of the growth. The decay will also be the same. The only issue will just, you will have a minus there. That's what will actually happen with this. Now, we are done with the little bit of an analysis that we got up to this equation as the general equation that you can actually use, that will always help you out. If this is t is in years, and this is the number of compoundings per year, and this is the number of compounding per year, and this is the interest per year. So this is the formula you actually use. Now, let's go back to our original equation, which was let me do this. I'm gonna do that, and then I'm also gonna do this, just to go a little bit back. If you look at the equations we found, we said that let me use this. If you have exponential, you have an exponential growth, and then this side you have exponential decay. Right. I'm gonna go back to the actual equation there. I don't want to make this complicated. I just want to make it as easy as possible. Remember that for this one, we usually have this. I can decide, maybe I'm just gonna say this is just gonna be my t, and this is just gonna be some I. It's fine. So we end up, we had this t is equal to n naught, and then you have 1 plus I raised to t, and then here you end up having n of t is equal to n naught, and then you have 1 minus I raised to t. Now, if you look into this particular equation here and that equation, and you want to change the base of this. You don't want to use this base, you want to use the Euler number. So we can always change this. We said that I can say that, okay, I wanted this to change it to be n of t is equal to n naught, and then if I want to change this, you can go and check the previous lesson we had on the conversion of bases. I think it's supposed to be lecture 18 if I'm not mistaken. So we're supposed to have e, which is the Euler's number or Nepler's constant. This is supposed to have some constant there. I'm going to call this constant r times some t. Right. But if I'm just doing that, you will just ask me, where is that 1 plus I? Where did it go? So I don't do that. I just be like, okay, if I want to change this, this is always going to be log, because I don't want to change everything. I just want to rewrite it. So I will have an e there, and then inside I will have 1 plus I times some t. This is what this thing will be. And you know that log e is the same as ln, so we'll end up having n naught, and then we're going to have e, and then raised to ln of 1 plus I raised to times t. So this is what is actually happening here. And then I can say this whole thing is going to be n naught e times rt, right? That constant is just rt. And then the same thing here, I can just say I'm going to have n naught, and then this thing here is going to be the same. If I am changing the bases here, I'm going to have n of t is equal to e. No. I'm going to have n naught because it's still there. I'm just changing the base. This is not the base. That is the base. So I'm going to have e raised to log e, and then you have 1 minus I raised to some t. No, not raised to, times t here. And then if you work this further, you will find out that this is the same as n naught, and then you're going to end up with e, and then this is going to be ln 1 minus I raised times t. Of course, I will talk about this a little bit at a later stage. Now, what is basically happening here? So I can either have this or have this equation for the growth. And also, if you look into this, this here is usually called growth. People usually call it in different words. Other they're saying is relative growth rate. Others are saying it is a growth constant. It depends on who is actually dealing with this. They call it growth constant. Now, let's look into this number here, because I am plusing from 1. If let's say, let me go down a little bit here. I want to draw a logarithmic function. We know that an exponential usually goes this way. If you have y is equal to a to the exponent x, and the base is bigger than a 1. If you look at ln here, at this log here, e is 2,718, which is bigger than 1. So the exponential function goes this way, and then log of that will actually be going this particular way, and here we have a 1 there. Right. Now, if I am adding a value from 1, which is positive, I will get a value this side. In other words, this is log e of some x here, which is the same as ln of x. So if I'm adding a value that is here, if I'm taking a value here and I plug it in the value of x, I will get a positive value. So this r here is positive, right? So I will get a positive value. So that is why this one is always gonna be a positive value. So we're gonna have a positive value here. So r is positive. Let me write it here. R is going to be positive. because this value, once I take a value and then I plug it here, I will get a value positive. So our R here is going to be a positive number. Now, if we come to this side here, I'm gonna say that we're gonna have N naught, and then we're gonna have E raised to some R, and then we have a T. R is going to be that. I have a value 1 here. I'm subtracting a value that is positive here. So I will get a value that is less than 1, but still bigger than 0, because the interest is always a fraction of 100. So when you're dividing a percentage by 100, you're always going to get a value less than or equal to 1. So we will get a value that is in between here. So whenever I take a value that is somewhere here, I plug it in this function, I will get a value that is less than 0. So I will get a negative value. So our R here, we say it is a growth rate constant. So we wanted to have to rewrite this and using a rate that is positive. So because here when I pick a value here, I always get a negative answer here. This equation is always written in terms of N naught E into minus K times T, whereby now this K is the one that is called relative growth rate, right? Or a decay constant. Decay constant. Because we wanted this K that we have here to be a positive, to be we wanted this, remember that this is going to be a negative value here, right? It's a negative value. So since it is a negative, I am taking that negative out such that this one here is a positive number. That's why we always have that negative there. We wanted this to be a positive number so that we can call it relative growth rate or a decay constant. That's what is happening here. So now for the decay, for the growth, this side is growth. I have N of T, and N of T is equal to N naught into 1 plus I raised to T, or I can rewrite this as N of T is equal to N naught E raised to RT, whereby this is called the relative growth rate. And then this side here, I have N of T, which is equal to N naught, and then I have 1 minus I to the power T. Of course, this is for decay. And then here, I will end up having N of T is equal to N naught into E raised to minus some K T. I don't want to use the R, but this is where this minus comes in, so that our K is a positive number. Now, can we use this information that we have studied so far to solve the problems? Before we can go in there, there's two things that I want us to talk about here. The time, I'm talking about growth now. I'm going to take this side as growth again. And then this side here, I'm going to talk about decay. Right. The question would be, how long does it take for a quantity to double its size? How long does it take for a quantity to double its size? And then this side, we are saying, how long does it take for a quantity to be half its size? How long is it going to take for this to reduce to about half its size? So of course here, we're not going to do something different here. The formula is very simple here. I have N of T is equal to N naught, and then I have E raised to RT. and then this side I have n naught, and then it is equal to n naught, this is n naught. I have n of t is equal to n naught e to the minus kt. How long does it take? I want this to be double its size, so I want my n of t. Let me put a d there so that I know that how long does it take for td to be equal to, or what is the value of td such that this is going to be 2 times the initial value. And then this side I want to talk about n of t half. Let me put an h here. How long is it gonna take? So this is the time it takes for it to be half. I denote it by th. It's going to be equal to 1/2 times the initial size. So I want to find out what is the value of t in this formula here. So n of t, I want it to be 2 times n naught is equal to n0 e times r, but the value of t here is going to be td because it's the time it takes for it to double. And then this side I will have 1/2, and then I have times n naught is equal to n naught e raised to minus k times our t h, right? So it's going to be h in the value of t because the time it takes for it to be half. And then when it comes to this, now I have an n this side and naught. I can cancel it out, and then I end up having a 2 is equal to e raised to r times td. And then this side, this cancels out with that. I have 1/2 is equal to e raised to minus k th. And then if we continue here, you'll find out that whenever you have a number equal to a base raised to an exponent, you also have the same thing. You can rewrite this as saying I have an exponent is equal to log base, and then you have your number inside. So I'm gonna use this, I'm gonna rewrite this. This is written in exponential form. Now I want to write it in a logarithmic form. So I'm gonna take this exponent down, so I will end up having r times td is equal to log, the base is e and the number is 2 there. And then this side here I'm going to have minus k times th is equal to log base e, and then I have 1/2 here. And then we can proceed here and say, okay, I want td, this is the how long, the time, so we have td is going to be equal to log base e, and then you have 2 all over r. And then if you look into this side here, I'm going to have th is equal to log e, and then we're going to have 1/2 all over minus a k. If we go further, at this side you will find out that let me first proceed with this side, we'll come back to that. And whenever you have this, you can see that it is the same as log e 2 raised to minus 1, because 2 raised to minus 1 is the same as 1 over, to remove that, 1/2, and then you divide this by minus k. If you remember, when we were doing laws of logarithms, we said that whenever you have log a of x to the power b, you can always bring this exponent down to say you have b log a x. So bring the exponent down. Now I'm gonna bring the x exponent down, which is minus 1. So we end up having minus log e of 2 all over minus a k. And your final answer now will be t of h is equal to this, and this minus and that minus will go away, and then end up having log e. Log e is the same as ln of 2. Log e means ln, and then you have a 2 there. Or you can just say this is the same as just log e of 2 all over some k there, where this is a decay constant or a growth rate. And then this side you're just gonna have ln of 2 divided by r. So you have td is written in this form, and then you have th is also written as ln 2 all over some k there, right? So it is in the same format. Now this td is usually called doubling time, the time it takes for the growth to double its size. And then this one here is usually called the half-life. So when someone is saying the half-life of this, they are saying the time it takes for it to decay to about half its size is this much. And then now we have the half-life, and now just collecting things out, we still have n of t is equal to n naught, and then we're going to have 1 plus I raised to t, and then we said that this can also be written as n of t is equal to n0 e to the power some rt, where our rt is a lane. And then for decay, we have n of t is equal to n naught into 1 minus I raised to some t, and this can also be written as n naught, and then we're going to have ae minus kt. So we have this, where this one is called the decay constant. So we have these two things, and now we have td as just ln of 2. This is ln in the calculator, and then you divide it by this r there. And then whenever you have the half-life is associated with the decay, is going to be ln of 2 divided by some k, where k is a decay constant. Now, just a quick recap here for us to know. We said that if I take the change, right, the change at any moment in time, it must be a constant. So the change at any time, if let's say this time is t is so small that the difference is in kind of seconds, so we can say that this change here is actually an instantaneous change, or the change that is actually happening at that particular point. So if you pick 2 points that are so close as if you have picked 1 point, then the change per unit time we usually denote as dn of t, or with respect to time. This is the change of this function at some time t. So if we take that change and then we divide it by n of t, remember that we said that this one is always gonna be some constant. So we say that if we use this particular equation here, this must always be equal to some r. In other words, if you want to find the growth rate at time t, in other words, nt with respect to time is supposed to be r times nt. So this one is usually called the growth rate is the growth rate at time t. So in other words, it is the derivative of this function with respect to time. So if I'm deriving this is a constant, I can pull it out, and the derivative of e is always e to that t, and then you take the derivative of that is r. So you will end up having this particular equation here. So for those who have done a derivative sense, this is how we go about this dt. We say dnt with respect to dt, this is always going to be n0 times e to the power t. So the derivative of e is always going to be that. That's why we usually change to this basis, because it's easy like that. And then the derivative of rt with respect to time is just going to be r, because t is just going to be that one there. And then I can take this r up front. I'm going to have n0, I'm going to have e, and then I'm going to have rt. And if you look into this particular expression there, this is just the same as nt. So we replace that by nt, and then you end up having your nt this side, and then this side the derivative of nt divided by dt, you end up getting this. So this one is called the growth rate at time t. But for those who haven't yet done the derivative, this is how we actually look into it. We actually look at the change of this particular function at some point there, 2 points that are very close, and you divide this by this fraction. It's supposed to be some constant, and that constant is going to be r. It's supposed to be the growth constant because this function is growing, so it's supposed to be some constant r. This is kind of the same as what we were doing here when we're deriving, saying that we have this change here, and this change here we divide it by this, multiply by that, but this change here we say it is I. But now we are using a different equation, so we actually say that this is going to be our r. So this is how we end up going about this. So we have some nice equations here. I'm just gonna make them blue, green. So we're gonna have this is our growth rate at time t, and then we also have this, which is the doubling time, or the time it takes to double, and then this one here we call it the half-life. So this equation you need to know it by heart, or need to know how to derive it. This equation, that equation, you need to know by heart or derive them. And then also these basic equations here, where's this equation and that equation, those are the equations that you need to know by heart. Now let us go back to actually solving the problems that I promised you that we're going to solve. So we had this problem here. A bacteria culture grows. If it grows, it means that we are using exponential. So we're supposed to have exponential. We have exponential growth. It grows, have exponential growth. Don't have to think about anything else. And exponential growth has equations. It had two equations. So it grows. It has two equations. One equation is n of t is equal to n naught into 1 plus I raised to t. The second one is saying n of t is equal to n naught, and then you have e raised to rt, where this is a constant relative growth rate. Grows exponential, so we have these two equations with constant relative, so we have this relative growth rate. So this one does not have constant relative growth rate, so this is the equation we'll be using. The bacteria count was 400 after 2 hours and 12. But this pen is actually disturbing. Let me try and redo this. So grows means we have, let me change the pen. Grows means that we have exponential growth, and then relative rate, which means we are using n of t. N of t is equal to n naught e raised to rt. This is the equation we're going to use. And then what is the relative growth rate? Express your answer in the percentage. So we use these two equations here. Let me add a page here, a page after. So basically here we already know that the bacteria count was this after 2 hours. So using that equation, I have n of t is equal to n naught e raised to rt, and now the first part of the sentence saying 400 after 2 hours. So n of 2 is equal to 400. That's what this statement is saying, where t is in hours. And 25 after 6 hours. This is the second statement, is saying n of 6 is equal to 25,600. Others they like to say 250, 600, but doesn't matter. What matters now is that how can we find the value of r? All we need to do here, we just have to say that, okay, if t is equal to 2 in this equation, I know the value of nt. So I'm just going to say n of 2 is equal to n naught, and then I have e raised to r, and then t is equal to 2. So you can see that n naught, I know n naught, I mean n2 is just 400. So you're going to have 400 is equal to n naught, and then you're going to have e raised to 2 times r. So I took this and then I replace n of 2 with it. And then if I'm working on this carefully, I can even work out n naught here and say my n naught is equal to 400, because I'm dividing on both sides by this, and then I will get 400 divided by e raised to 2r, and you can call this equation 1. And then let's go for this one here. So if t is equal to 6 hours, so n of 6 is equal to n naught e raised to r times 6. T is 6 hours. And then what will happen here? This is 25600 is equal to n naught e raised to r to the power 6. And then now you will see that I have 25600 is equal to n naught. What is the value of n naught? From equation 1 we have n naught. N naught is 400 divided by e raised to 2r. So I will have 400 divided by e raised to 2r. This is the value of n naught. So I replaced this n naught by that value there. And then now we'll end up having, this remains the same as e raised to 6 times r. R times 6 is the same as 6 times r. And if you proceed with this, we have 200, 600, and then we actually have 400, and then this is, I'm just going to move this here because this base and that base is the same. So we'll have e 6r all over e 2r. And if you look carefully to this, whenever you're dividing powers of the same base, we subtract exponents. So we will end up having 25 600 is equal to 400 e raised to, this one here will be 6r. We're going to have e raised to 6r minus 2r. Whenever you're dividing powers of the same base, you subtract exponents. 6r minus 2r is going to be 4r. Right. Once we have that, let me add a page here so that I can continue. I can see that I have 256 times 100. These zeros are saying I'm multiplying that by 100. This side I have 4 times 100. I have e raised to 4r. This 100, 4 times 100 is 400. 256 times 100 is 25,600. So this 100 here and that 100 is on both sides, so I can cancel it out. And now I am left with the 256 is equal to 4e raised to 4r. And now I can divide both sides by 4, divide both sides by 4, and then this 4 and that 4 will cancel out. And now we end up having 256 all over 4 is equal to e raised to 4r. We have a calculator here. We can just take this number and divide by 4 and see what we are getting here. Or we can work it out by hand and say that how many 4s do we have out of 2? We have 0 of them, so we proceed and say 25. How many 4s do we have out of 25? You can see that we actually have 4, 8, 12, 16, 20, 25. So we actually have 6 of those. So we're going to have 6 here. So we have 6 4s out of 25. And then the remainder is 1. And then we ask ourselves, how many 4s do we have in 16? and we find out we have a 4, and then this is supposed to be equal to e to the power of 4r. And now that we have that, or you can just say use a calculator, 256 divided by 4, what is the answer? It's a 64. So you can use a calculator if you want to. But now this is a number, this is an exponent, this is a base. I want to bring the exponent down. I have 4r is equal to, whenever I'm bringing the exponent down, I must have a log and the base is e, and then now I have a 64 inside. Then r is going to be equal to log e 64 all over a 4. That's what is nice about this r now. But the question did not say find r, it just say find the relative growth rate, which is r. Express your answer as a percentage. So because we want to rewrite this as a percentage, so our r is just the same as log e, and then you have 64 divided by 4, and then you multiply by 100. Because this was a decimal, now we want to multiply by 100% to get a percentage. So our r is approximately equal to, if you don't have a calculator, you can just say how many 4s do we have out of okay, you can just say how many 4s do we have in 1? We don't have any. How many 4s do we have in 10? We have 2 of them. 4, 8, and then we have a remainder 2. And how many 4s do we have in 20? We have 5 of them, and then you just say we have 25 log e 64%. So this is r in percentage. Or we can just use a calculator, multiply by log base, I want to place in e, and then there I have a 64. What is the answer that I'm getting? I end up having, this is 103.97%. So I've just rounded off into 2 decimal places. So with the r, it's possible to have a value that is bigger than 100 in percentage form compared to I, but I is always less than 100 because it's just the change. But this one is the rate of increasing, so this is actually bigger than 100 if possible. The second question, what was the initial size of the culture? We are looking for n now. So because you already found r, what will be n? N naught. Initial size, so you're gonna end up having my n naught using equation 1 is going to be equal to 400 divided by e raised to our r. Our original r, if you look into it here, where's our r? Our original r was log e 64. Our r was log e 64 all over a 4, and then you multiply this by 2. So multiply this by 2, so we'll end up having 400 divided by e raised to this is going to be half, right? So we'll end up having this is going to be half, so you'll end up having log e, and then you have your 64, and then all over a 2. Let me write it in a cleaner way down here. Just gonna try and rewrite it here so that we can see and copy it. So our n naught is equal to 400 divided by e raised to log e, and then you have a 64 all over a 2. But if you look into this, you can just press in the calculator, or you can use log, the rules of logarithms. So you have 4 divided by e, and then this half here is half. I can put it inside. I'm gonna have a log and then e, and then I'm gonna have a 64 raised to 1 over 2, or the square root of 64, and then we will end up having 400 divided by e raised to log e, and then inside 64 we're gonna end up having an 8 there. So you can end your answer like this, or you can press in the calculator there, and then you can get your final answer. So just for curiosity, you can just press 400 and then you divide that by e. Where's e? E, and then you raise that to log base e, or you can just say ln of 8. So your answer is going to be about 50. So your initial value here is supposed to be a 50 here, right? But if you look into this, actually we can actually work this thing out. I'm just realizing it now. If you look here, we have an e, so this e and this log e will cancel out, and you're left with 400 divided by 8, right? And then 400 divided by 8 is just like this. How many 8 do we have in 4? We have none. But how many 8s do we have out of 40? We have 5. And then there is actually no remainder. And then how many 8 out of this? We have 0. So actually n0 was actually a 50. You can see or press with a calculator, you will get that. One thing to notice that log e, we have a base e, we have a log, and we have e here. These cancel out and you're left with an 8. You can press a calculator. So we have an n0 here. And now find the number of cells. Okay, find an expression for the number of bacteria after t time t. So for this one, all you need to do is going to be n of t is going to be n0, and naught is 50, and then you're gonna have e. What was our value of r? The value of r, what was r? R was this 64. No, it was this 64. We can place this as it is, or we can actually try and see if we can work it out. This 64 is the same as this is supposed to be, I worked it out to be log e, and then we ended up having an 8 inside. If you look when we're actually working with this here, we worked it out. No, this is not supposed to be it. This one is because we multiplied by 2. So this one, if we are continuing to work it out, let me work it out on the side here. End up having log e, and then this is going to be 8 squared, this is 64, over a 4, and then I can bring that one down, and then I will end up having 2 log 8 and the base e, and then all over a 4, and then I'll end up having 1 over 2 log 8 e, and then this is just gonna be log e, and then you're gonna have the square root of 8. It's not actually not helping anyone, this one, but you can have it. So if let's say now we're actually looking for this, it's going to be exact as it was. So we are just gonna place here log e 64 all over a 4 times t, because this is our r. So this is the equation they are actually looking for here. That's the equation we are looking for here. We're just replacing what the value of r here and the value of n naught. So that's what we were actually looking for here. Now, when it comes to find the rate of growth after this, so what you actually looking for here, the growth rate. First, you want to find out what is n of 4.5, and then once you have this n of 4.5, and then you find it, and then you're just gonna multiply this by r. That is what they are looking for. So in this case here, you can just say you want your r. Our r was we had our r here. Our r was just this is r, so we ended up having a log base e, and then we have a 64, and then after that we divide it by 4. That's our r. And then now we want to multiply by n of 4,5. So we're gonna have times, I'm just gonna place a 50, and then I'm gonna shift e, and then I raise this e to log. I'm just gonna place this, and then I place inside 64, and then that whole thing is divided by a 4, and then I multiply that whole thing by t, which is, I'm just gonna say times 4,5. What will that value be? So that's the value that they are looking for here. So you just want to find this is this part here, and then we actually continue in that particular fashion, just to write so that you can see. So they are looking for dn of 4,5 with respect to time. So this is going to be your r times n of 4,5. And what was our r? Our r was just, we found it to be, our r was this. So we had log e, and then it's 64, and then you divide this whole thing by 4, and then you multiply by that. So we are substituting this 4,5 in this. So we just had 50, and then we had e raised to log e, and then you have 64 inside. You divide this by 4, and then you multiply by 4,5. Your calculator should be able to solve this. If you don't have a calculator, all you need to do here, this is a multiplication, 4,5, which is 4.5. So you can just work this one out, sort it out, and then after that you can keep working this piece and that piece one by one until you actually arrive to your answer here in a fractional form. So that's how you actually solve this piece here. When will the population reach 50,000? 50,000. So here you're gonna have for f, what you're gonna say, I want 50,000 is equal to 50 times e. So this value here is given. You are looking for t. You already know r, you already know n naught. So n naught was this, r was log e 64 all over a 4 times some t. So you actually solve for t for this particular problem here, but just for a for the purpose of this particular video here, if let's say I have a 0 here, I can solve this. Let me write at the end of this. Where's this? I'm just gonna add a page here, or I can just minus this. Actually, I'm not gonna gain any space here. Okay, let me just add a page after. Okay, so we said that when how long will it take for it to reach that? So we wanna have n naught e to rt. This one is given to be 50,000, and then this one we found it to be 50, and then we have e, what is our r there? Our r we found it to be log e 64, and then you divide by 4, and then our t is what we are looking for. I have 1 0 there, I have 1 0 there, I can cancel it out, and then I can divide both sides by 5. I will have 50 or 5,000 divided by 5, and then is equal to e raised to log e, and then you have 64 all over a 4 times t. And then what is the answer here? I have 5,000 divided by 5. How many 5s out of this 5 here? You can see that we actually have 1. So 5,000 divided by 5 is just actually 1,000. There's nothing to do. There's no need to actually be smart about it. You have log e, and then you have 64, and then you have t all over a 4. Then I'm solving for t. I have to bring this one down. I will have log e, and then I have 64, and then I divide that by 4 times t. This is going to be equal to log the base, which was e, and then inside I will have 1000. Now that I have that, can I solve for t? So our t is just going to be log e 1000, and then you divide this whole thing by this chunk here as it is. So this chunk is going to be log e 64 all over a 4, and then you can punch your calculator. It's going to give you answers. If you don't have a calculator, you leave it like that. Of course, we can just I'm just gonna leave it like that. I was just trying to illustrate how you actually go about this, that you are just using the formula, nothing much. You just use the formula, you keep punching in the numbers, and now the population of a microbial culture grows by 2% every day from the initial value. So we have this is every day. Which of the following exponential function describes the culture population at any time? So we have this percentage here. If you look into this percentage, is less than 100. And not only that, is every day. This is not the growth rate, it's our I here. So for this one, you use the equation n of t is equal to n naught, and then have 1 plus I raised to t, and then n naught is not given here. We're only given a percentage, so we leave it as n naught. 1 plus I. This one is 2,5. 2,5, we want to convert it to a decimal because we don't want a percentage here. So you're gonna have 2,5, and then you divide it by 100%. You have how many zeros here? You have 2 zeros. So what I usually do here, I usually add zeros both sides, as many as I can. And now if I am dividing, which means that this comma here is moving to the left. But if I was multiplying, this comma here was going to move to the right. Now this 100 here, it has 2 zeros, so I'm gonna move this comma 2 times to the left. So I'm gonna move it 1, 2. So I will take this 0 in front of this comma. So here I will have 0 comma. How many zeros in front of 2? I will have 0, 1, 0, 2, 5. And then you raise it to t. And then 1 plus that is going to be n naught. And then you're going to have 1 and 0. 1 plus 0 is 1. And then the comma there just go there as it is. So you have a t. Now which of these looks like that? Because it grows, we must have a plus, not a minus. So this one is not the one. This one is not the one. This one is not the one. What about this one? This one is not the one because it does not have an n naught here. And this one is the one actually we are looking for. So that's how you select here. And this question here is saying, suppose the exponential function we take with the population of microbiology in 2 is written as an exponential function with the natural base e, the Euler number. What will be the growth rate? So if, let's say, we change this, we want to rewrite it in an exponential form, it would be n naught, but with base e. I want e, and then when you are changing this base, is going to be log. I had a base e, it has to be the base there, and then whatever is inside there, it has to be 1,025 times t. But whenever you have log e is the same as the natural log. So we're supposed to have e raised to a natural log of 1,025 t. Now if you look into this equation was supposed to be n naught e raised to rt, and the growth rate here, or the growth constant r, is the one that is here. So this is the value of r that they are looking for here. So we are looking for ln of 1,25, which is in A. So that's what they were looking for here. What is the growth rate? That's the growth rate here they were looking for. The constant growth rate. Right. Now, a decision is made to invest 40,000 for 4 years. The money earns 12,000 compounded monthly. Now, what do we actually want to achieve here? Actually, this question is not enough. It's not complete. They were supposed to say find the value of the investment. Find the value of the investment after 4 years. So that's how this question was supposed to look like. Now that we have this for 4 years, of course, you invest this much. When you are investing, you want the money to grow, or you want it to increase. So if you want the money to grow or increase, then we are using this formula for exponential growth, which is a naught 1 plus I raised to some t there. The time is going to take after 4 years. Now, what is N naught? N naught is the amount that you are investing. So you're supposed to end up having 40,000. And then 1 plus I. What is I? I is 12%. So I have 12%. I want a decimal there. I have to divide by 100. Now, whenever you have just a number, you must know the comma is somewhere there at the end. So you have 12,0 is the same as 12. Of course, I always add as many zeros in front, as many zeros after this comma here, 12. Now, if I'm multiplying, the comma will be going to the right. But if I'm dividing, the comma is moving to the left. So I have this comma here. I have to move it to the left. How many times? You ask yourself, how many zeros in the denominator? I have 2. So I'm going to move it once, twice. So I'll end up having 0, comma, this 0 here. Comma 1 2, because the comma is just in front of a 1, so it's comma 1 and 2, and then at t we're supposed to have 4 years. So this is how you actually solve this problem. If we don't have this issue here, which is compounded monthly. Now, compounded monthly is simply saying that you are getting this percent per annum, but you are receiving a fraction of it every month. So you have 12% every month. So this is 12. But we want to give you a slice. Now, how many months do we have per year? We have 12. So you divide this by 12. And then we have 4 years. How many months do you have per year? You have 12. So you're supposed to multiply this by 12. So multiply this by 12, because in year 1 you have 12, second year you have another 12, and another year you have another 12. That's why you multiply there. You want to convert this compounded monthly, so this number of years you want to convert it into month, and then this percentage here you want to take a slice here, so you will end up having a nice equation like this. So you have that 40,000 there. And then this one is going to be, if you look into this, how many of these, this is supposed to be, you have 0,12, and then you want to divide this by 12, so you're supposed to be 1 plus, this one is supposed to be just 0,01. That's what's supposed to be, because this, if you take this 12% here and you divide it by 12, you would get a 1%, and a 1% is 0,1, and then you raise it to 4 times 12, you have 12, 24, 36, 48, this is supposed to be 48, and then of course, the only thing that you can do here is to just combine these two here, which is 1, 0,01, and then you raise it to 48. That's how you solve this particular problem here. And this one, the half-life of a carbon is approximately this number of years. If a sample originally contains 200 grams, now contains this, how old is the sample? The half-life is given. Half-life, which means this thing is actually decreasing, so we want to use decay. So we will end up having n naught, nt is equal to n naught, and then after having n naught, you can either have 1 minus I raised to t, or you can have n t is equal to n naught, and then you have e minus some kt there. So you have this equation on that. Now it depends now on which equation is actually going to help you to solve the problem. If you look into this equation here, this equation does not usually talk about half-life, but this one is the one that is actually talking about half-life, so we're gonna be using that equation there. And now we just want to find the value of k using the half-life. We know that th is just equal to ln of 2 divided by some k there. Or if you cross multiply here, this goes there, this goes down this side, you will end up having k is equal to ln 2 divided by t of h. Remember that the half-life is given, in other words t of h is given, so our k is going to be ln of 2 divided by 5730 years. So that's our k. Now I'm gonna add a page here, page after. I'm also gonna add another one, page after. And if you look into this, we found our k. So we have n of t is equal to n naught e raised to minus ln of 2 divided by 5730 times t. So we have this. Okay. The sample originally contained 200 grams. Originally it contained this much, which means n naught is this much. We go back here and we say our equation actually is having 200 e raised to minus ln of 2 all over 5730 t. We have this, so this is the formula here. We have n of t originally, which means n naught. Now it contains this. How old is the sample? So what they are saying here, if n of t is equal to 20, what is t? So this is the t that we're looking for here. So I'm gonna take this and place it there. I'm gonna end up having a 20. End up having a 20 is equal to 200 e minus ln of 2 all over 5730 t. And then I have a 0 there, and the 0 I cancel them out, and then I have 2 is equal to 20 e raised to minus ln of 2 all over 5730 t. And then if you look into this, I'm going to divide by 20 on both sides, so I have 2 divided by 20 is equal to e raised to minus ln of 2 all over 5730 t. Now if you look into this, this one is always gonna be, how many 2's out of 2? You have 1. How many 2's out of 20? You have a 10. And this is just equal to e raised to minus ln of 2 all over 5730 times 80. Excuse me. Now I have a humongous exponent there, I have a number there, I have a base. So minus ln of 2 divided by 5730 t is just equal to log the base e, and then I'm gonna plug in inside 1 over a 10 here. And then of course my t here is going to be equal to, I'm just gonna say log e, and then I'm gonna have 1 over 10, and then all over here you can even cross multiply if you want to, but I'm not gonna do that. I'm gonna have a minus ln of 2 all over 5730. Now if I'm dividing by this, I'm changing the division to multiplication. When I'm doing that, I can switch these two around. So I'm gonna have log e and then 1 over 10 times 5730 all over ln of 2, which is negative. Now, what I want us to do now is very simple, just collecting these terms in a nicer way. Someone might say that we have a minus here, our time will be negative. That's not actually true, because this log here, log e, inside I have 10 raised to minus 1. 1 over 10 is the same as 10 to the power minus 1, and then times 5, 7, 30, and then all divided by minus ln of 2. And then if you proceed with this, I'm going to add a page there. If you proceed with this, you will find out that you have minus. I'm taking this out. This is an exponent. I can always bring it in front here. I will have a log e, and then here I will have a 10, and then divide here by minus ln of 2, and then times 5, 7, 30. And if you look into this minus and minus will vanish or go away, and now I will have log e, and then here I have 10 in the numerator, and the denominator I have ln of 2 times 5, 7, 30. Just for taking or playing around with the logs, this you can punch it in a calculator, but I want to play along with these logs here. If you want to play along with this is log e10, and then if you look into this here, this is the same as log e of 2. Ln and log e, one and the same thing, so you're gonna end up 5, 7, 30. And then I have this nice base here, I have this same base here. This means now, if you remember when we were doing logs, we said that if I have log a of x, this is the same as log a, no, that was the last law we used. This is the same as log sum b of x all over log sum b of a. This is any base. You can place a 10 or 10 as long as b is greater than 0. You can place any base here. This, as long as this and that is the same, I can always take what is in the numerator and in the denominator as a base, and this in the numerator as a number inside. So here, this is the same as log. What was in the denominator will be a 2, and what was in the numerator is going to be a 10. This was what in the numerator. And then I multiply by 5, 7, 30. So this is going to be 5, 7, 30 times log 2, and then you're gonna have a 10. So that's supposed to be your final answer, or you can punch it in a calculator. You have a 5, 7, 30, and then you multiply that by log, you have a 2, and then there you have a 10. So you end up having some nice things there. I think I'm supposed to have made something of that kind there. Supposed to have something like that. I think so. So for now, I think that's all about these questions. I will end up there. Try some other questions and see what you are actually getting, and then we'll see what we can